So how's this going to all fit in? Well, I guess I'll give the talk and we'll see how it works. There's an interesting addendum to what we were saying, but we'll come back and see if anyone in the audience spots that in a minute. So what I wanted to, giving this talk made me think about what do we mean by time in current cosmology, because we kind of tend to be working at the coalface, we're busy working on computer code, improving it. Nobody really thinks about what do we mean by time in modern cosmology. So it was very useful to take a little step back and think about how our notions of time have changed. And what I'm going to base my talk on is a lot of numerical simulation work. So I'm going to show you some movies, because it's getting late in the day, and somebody once told me if you're giving the last talk of a meeting, you better have a good movie. So, boy, have I got a good movie for you. And what we do is we try to simulate the creation of the cosmos. Now, the great thing that we're able to do now is we understand, or we think we understand, the laws of physics. So if we apply those laws of physics, we can program up the computer, we can press go on the computer, and we can see how the universe should develop. And we've recently been making a lot of progress in trying not to just create the kind of big structures of the universe that you see here, so this kind of cosmic web of structures, but also to go and create individual galaxies within the universe, so the individual collections in which you find stars. And so this is a large-scale view of our little piece of universe that we've made. It's about 50 megaparsecs here, so that takes light to cross this box about 150 million years. And I'm going to zoom in on a little patch here. And if I blow up this little patch, there's enough information in the computer that I can then blow up another tiny little patch. And if the screen was slightly better, you could see this is actually a galaxy like our Milky Way that's formed there. So I love going to astronomical societies and showing them this picture. And I usually show them this picture, and they go, oh yes, last night we took a photograph of this one, and oh yes, last time we were photographing that one. Then I point out that these are all galaxies found inside the universe that we've created inside the computer. It's just really astounding that we can get to this kind of level of reality by programming a computer with the laws of physics. Now, I think at this point, what I need to do is talk a little bit about the history of the universe, because I was trying to guess how much people in the audience would know, but bear with me if you already know this, and slow me down if I'm going way too fast. So, how do we do this? What are the stages that really happen in our modern universe? Well, the universe starts with what's called the Big Bang, but now we kind of have an idea of what we don't know about the universe. So you can go and you can try to compute when do the laws of physics break down. And if you go back in time to when the universe was earlier and earlier and earlier, because of the expansion of the universe at very early times was very hot and dense. And you have two important theories that play a big role in shaping the universe we're in. You have gravity, which we can do with Einstein's general relativity, and you have quantum mechanics. And one of the great predictions of Einstein's relativity is the existence of black holes, things that are so dense that nothing can escape them, not even light rays. And at the same time, you've got the great theories of quantum mechanics, and that tells you if you look on really small scales, you can't know both the position and the velocity of something. So if I try to zoom in and look at something really very detailed, eventually I won't be able to do that. And so we know when things go wrong when I have a black hole that's so small that I don't know where it is, essentially. And you can actually go and calculate that, and it comes up with something called the Planck scale. And you know that the only way to understand that would be to have a consistent theory of both quantum mechanics and general relativity. And that doesn't exist in a way that we understand what it means. People have proposed such a theory, but then trying to extract anything from the mathematics proves impossibly difficult. So we don't know how the universe begins, but a good idea is that at the beginning of time there was no time because of this uncertainty in everything, that there was basically just a foam of stuff. It has a lot of resonance with what Neil was talking about, the infinity of God. Oh, I better not go there, that's dangerous. But, so there is no time, it just exists. And then out of this space-time foam, a little piece manages to last long enough that it begins to grow because of its unusual high energy. And the growth of that little point allows it to blow up like a balloon. And that's kind of how we understand the beginning of the universe. Now, it's a story. How do we know what it looks like for real? Well, fortunately, the theory of this we can write down. It pushes our knowledge of the equations, but we can predict how the universe would expand. And one of the predictions is that the universe would not be completely uniform, would be full of little tiny irregularities in it, okay, arising from the fact that this was a quantum process in the first place, so it's not got a certain single value. Now, luckily, trying to compute those would be impossible, but luckily we can now observe these. They leave an imprint on a very distant universe. And so when I say we're going to compute the history of the universe, I can't start at the very beginning, but I can take these small, tiny irregularities and see how they would grow over time. Okay. And the idea is the universe then, because of this high initial period of inflation, and continues to coast outwards. It gets larger and larger, and as the universe expands, that's also equivalent to cooling it down. Okay? Just as if you feel the air coming out of an air pump or something like that, the air is actually very cool as it's expanding. And the same process is happening in the universe. It's getting very cooler and cooler, and that turns the initial raw energy of the universe into the actual particles. Okay. So this process of the expansion of the universe is then very important, and what's going to happen is the gravity is then going to be able to collect these particles of matter together to form structures. So I can now start from these initial small fluctuations, turn on the calculation of gravity. I know how to do that well, and let the computer do its job. And so this is a little part of a calculation showing this, and you can see how you build up this web-like structure of the universe, okay, over time. Now, this makes a nice picture, but it's kind of a little bit deceptive, because what we always do, and what we tend to forget in modern astronomy, is this is really expanding as well. So I've taken a little cube, but that cube is actually growing over time and getting bigger and bigger. And I've also done tricks to make it look like things happen at a uniform rate. They don't happen at a uniform rate in terms of if I sat and had my watch and watched the structures of the universe going past, they wouldn't form at a uniform rate like they do in this movie. So, that kind of means that in cosmology, we're reinventing what we mean by time, and I think we don't normally acknowledge that, right? It happens just because computer code gets written in a certain way. But in practice, what's going on is we might normally think of time as being a measure of or astronomical time at least, be a measure of how long it takes things to go round and come back to where they were in the first place. Be our common notion of time. So for instance, we know how long a day is because the Earth goes around. We know how long a year is. Okay. But what happens in cosmology is because the universe is expanding, everything is getting less dense over time. And so I can simulate that using Keynote. Right, I think that was a bit challenging for PowerPoint, but here you go. So this is a simulation of the expansion of the universe, and basically all the time scales now take an awful lot longer. So the universe kind of, as it expands, slows down, and things take longer and longer to happen. So cosmic time scales are not constant. So our ideas about time, implicitly in cosmology, we tend to think about things in terms of this time scale, which is related to the density of the universe. So it actually means as the universe expands, the density here in this formula is going down, so the time scale on which everything is happening is longer and longer, and the universe slows down. Okay. So this introduces the notion then that rather than thinking about time in the usual way measured on my clock, I can maybe think about time as being the expansion of the universe and how the universe has grown over time. And we often measure this then, what in computer codes becomes important is the expansion factor of the universe. How big is the universe relative to its initial size? Okay. Now, luckily, it's possible, one of those miracles of the way the universe is set up, that as the universe expands, light gets stretched. So if I look at a distant object, I can see, in this case, an emission line due to the molecule of hydrogen. And I know from looking at lots of spectra like this, that this line is really the Lyman alpha transition of hydrogen, which should have a wavelength of about 1260 angstroms. And I look at this observed spectrum, and I'm seeing this transition is now occurring at a wavelength of almost 5,000 angstroms. So what's happening? Well, it's the expansion of the universe has expanded the wavelengths of these oscillations, and so I know, I can call it, this is what's called the redshift, I know how big the universe was when that light was emitted compared to now. So it's really quite remarkably convenient that I can kind of now, by observing this distant object, actually look back in the past and see what things were like when the universe was much smaller. And I've got access to that information directly. Of course, I need a big telescope to do this because I'm ever wanting to look further and further into the beginning of time, which means that the telescope has to get larger and larger to be able to make measurements like this. Now, the other thing whilst I was putting this talk together that occurred to me is, what happened to all the questions about general relativity, causality, all those kind of nitty-gritty questions raised by Einstein's special relativity? Turns out they're weirdly irrelevant, because once you take into account the expansion of the universe and rewrite the equations in that reference frame, everything actually looks like it was written by Newton. Okay, there's just a little subtlety to how you interpret some of the numbers in the equations. So we don't have any of these causality issues with time, which is kind of weird, you'd have thought, with the cosmos. Okay, so that was a little bit thinking about time, and if you put this in the computer, you end up with movies like this, forming a nice object at the center of this little patch here. This is actually quite a zoomed-in view compared to everything you've seen so far. And we know that the universe now is mostly filled with matter that you can't actually see. So somebody came up with a clever term of dark matter for this mass. Ringel has invented this colour for dark matter, so I think when it's discovered, we're going to discover it's this kind of pinky, yellowy colour, and the colours kind of illustrate the density of dark matter in the universe. And so if you had dark matter glasses that you could put on and look at the universe, it would look like this. We would have a good description and a good notion of time in the universe. Okay. Unfortunately, what we really want is to understand where the stars and galaxies are in this picture. And you can kind of guess, oh, well, I bet there's a big galaxy here. But the challenge is now to understand how did the galaxy actually get there at the center of this. And the interesting thing that's emerging from the work we do is this kind of competition that the way gas gets to the, or material gets to the center is kind of like this cartoon that I think I did in my PhD thesis, and it's amazing that it's still even vaguely relevant today. But that gravity assembles matter, but the matter it assembles is hot and diffuse, and stars are made up of basically fusion reactors that are incredibly hot, incredibly dense, so that the gravity can stop them blowing themselves apart. And so how does the gas get so dense? Well, the reason it gets dense is by emitting photons. Okay? And that cools down the gas. As it cools down, it then collapses into a spinning disk. And this is basically the story of galaxy formation. But the interesting thing is that there's a whole different time scale going on here. We had the expanding universe time scale that was collecting the matter together and bringing it into one place. But there's this competition, there's a different time scale. And this is related to quantum mechanics, and hence my claim, there's an atomic clock at work in the universe, determining how we go from the collected matter to the formation of the galaxy itself. Okay, so the universe's complexity arises from the interaction of these two things. So, for instance, this is a plot. Am I allowed to show plots in this talk? Well, I've done it, so it's too late. But this is the star formation rate of the universe, the rate at which the universe forms stars. It's a logarithmic plot, so the difference between the rate of formation of stars at the maximum of the universe and today is about a factor of 10. So the universe was a much more active place in the past, about 8 or 10 billion years ago.
So Richard, the present is the origin here.
So sorry, yes, thank you. So the present is over here, okay, and the beginning of the universe is over here, but a little bit further than this axis goes. Okay. And the observations are shown as these data points with error bars. Okay. And the simulation results are amazingly this black line. And there's a correction you need to add because we only can calculate a small part of the universe. And our estimate of that correction gets us to this grey line. So it's really quite incredible that we do so well at reproducing this plot. But the interesting thing about in terms of the nature of time is that there's a rise here in the rate at which the universe forms stars. And this is due to that atomic clock holding things up. The structures are being formed very fast, but stars form relatively slowly, and that kind of slows down the creation of stars. But then later in the universe, the accumulation of structure is declining, and so this is causing a decline in the rate of star formation